Hi students, so today we start optimization tutorial 5a. Today I'm going to look at convexity of the test function. This is the same function which we discussed in our tutorial 5 for which I found the stationary point, and today we are going to look at convexity. I'm Dr. Ganguly. Now just to recapitulate, remember the function had the form fx is x square plus e to the power minus x for the one-dimensional situation, and fx is x1 square plus 2x2 square plus e to the power minus x1 minus x2 for the two-dimensional realization. Now of course what we did is we extrapolated this to n dimensions and then we found the stationary point. Now today I'm going to discuss a particular theorem and then we are going to use it to prove convexity of this type of function. And this theorem would entail dividing a function like this into two functions. So you can see here there is one function which is composed of quadratic type of terms. We could call this one function and then the second function is here. Now it turns out that in many cases it's easier to solve these problems if we take recourse to this kind of theorem. Now if you are interested in knowledge of convexity, check out tutorial 4, also lecture 4 in the optimization lecture series for convexity, and also look at lecture 5 for a review of the basics. Of course, do remember that all the optimization lectures and tutorials are in my optimization playlist on the channel, so that's the full course. So the question one is, if qx and px are convex functions, is fx equals px plus qx also a convex function? So essentially in many situations you can have a composite function composed of two functions, and in those cases this kind of theorem is going to come in very handy. So before we begin this problem, let us just look at the definition of a convex function. So the definition can be written in form of this inequality here, that is the function value at this particular point is less than equal to the value of this point which corresponds to a line. So if we look at this function, let us say there is a function f here, then what would happen? We would have the value f of x at a given point, we would have the value f of y at a given point. So these points are x and y. And now if I look at any intermediate point, I can write that point as alpha x plus 1 minus alpha y if alpha lies between 0 and 1. So essentially by varying alpha I can go to all these points in the domain between x and y. So you can see the function value will of course vary depending on the value of alpha, and so on the left hand side we have the function value at all these points. Now on the right hand side we essentially have the value corresponding to points on this line. So this particular inequality essentially tells us that the curve lies below or on the line. So that's essentially what is meant by this inequality here. Now most of the time convex functions will have nice shapes like this, and they will have clear local minimum points which will also correspond to the global minimum point. But it's not in all cases that may happen, because remember there are some functions like for example the exponential function e to the power x which is convex but which necessarily doesn't have a nice minimum point. So that's something to keep in mind. So now let us continue with this proof. So we will say that we can write a function f as p plus q, and p and q are both convex. So in that case I can write this equation here. So I can simply write the function as p plus q, and I have essentially created this general point here. So remember, if x and y are 2 points, then alpha x plus 1 minus alpha y is a general point lying between these 2 points. Alpha varies from 0 to 1. So of course this equation is something which I immediately get, and now I am going to use the fact that p and q are convex. So because p and q are convex, I can write these two inequalities which I have given in purple, and you can see here these essentially say that the value of the function at a general point is less than the value of a line at the same point, and this again tells us the same thing for q of x. So essentially we have seen this is valid for p and for function q. Now these two purple equations, they come from convexity. Now I can take these two equations and put it in the first equation here, and then I obtain this particular inequality here. So what has happened is that the equal to has now been replaced by the less than equal to sign, and on the right hand side I have this particular term, that is alpha px plus 1 minus alpha py, and I have the second term here, that is alpha qx plus 1 minus alpha qy. So this is a nice inequality we have obtained, and then in the next slide I'm going to simplify this. So let us write down the expression we obtained in the previous slide, and then immediately I can realize that I can take the alpha values in the right hand side and I can lump the two terms together, so I get alpha and then I get px plus qx. Similarly, I can take the values corresponding to the 1 minus alpha term and I can write it in this form here. So I get py plus qy here. Now immediately I can realize that I could write this px plus qx as f of x and py plus qy as f of y. And so once I do this, I get this nice expression in green, and you can immediately see that this is the definition of convexity. So from this expression in green, we know that f is a convex function. So essentially we have proved that if we have a function f and we can write it as a sum of two functions p and q, if p and q are convex, then f is also convex. Now I'm going to use this to prove convexity for our test function. Now the test function is actually a sum of these type of quadratic terms and also an exponential term. So I'm going to split this function into two parts, and then I'm going to prove each part is convex, and if I do that, then of course the function f of x is going to be convex from the theorem we proved in question number 1. Now do remember that the simple realization of this function in the two-dimensional space is given in this form, and this is nothing but the same function in n-dimensional space, which we are going to use later in this course to check out different numerical methods. So now I have written this function here and I have split it into two parts, px and qx, and px is x1 square plus 2x2 square all the way to nxn square, and q of x is e to the power minus x1 minus x2 all the way to minus xn. And now let's try to look at this px and qx separately and see if they are convex. So first we start with px. This is the equation for px, and I have written out here ixi square and jxj square because that's going to help me differentiate and get a general term. So if I differentiate p with respect to xi, I immediately get 2ixi. Remember, when we take partial derivatives, we treat all the remaining variables as constant, and so only the term ixi square is going to get differentiated, and we are going to get this. Now if I take the next derivative, I am simply going to get 2I here. Now if I were to take the derivative with respect to xj, for example, the second derivative would be 2j. Now the interesting term is when we take the cross derivative, that is the second derivative of p with respect to xi and xj. So what I do is I take this term, which is the first derivative with respect to xi, and I differentiate with respect to xj. But there is no xj in this term here, so essentially this is going to be 0. So the Hessian matrix is going to be a diagonal matrix. Now you can see here all the diagonal terms correspond to 2i. So when I is 1, I get 2. When I is 2, I get 4. When I is 3, I get 6. And when I is n, I get 2n. And the off diagonal terms are all 0 because the second derivative of p with respect to xi, xj is 0. So from this particular Hessian matrix, I can immediately realize that the eigenvalues of this matrix are 2, 4, 6, 8 all the way to 2n, and all these are of course greater than 0 because n is greater than 0, and therefore this function p of x is a convex function. Now of course you can realize by looking at this function, even plotting some of its realizations with n is 2 or n is 3, that this is going to be a convex function because it's got the nice bowl shape also, and certainly the second derivative is positive in all cases. Now let's look at the second function, which is q of x, which is the exponential function. Now here again, when we differentiate this exponential function, say dq by dxi, we have to keep in mind that we are going to get the same expression back, that is e to the power minus x1 to minus xn, and we are going to get a derivative of this particular exponent with respect to xi. So that's going to give me the minus 1. So there is going to be a negative sign here. Now if I take the next derivative, I'm going to get one more minus 1, and that's going to remove this negative sign. So I get e to the power minus x1 to minus xn term here. Now since this kind of exponent term is going to take place all the time, I'm going to call this entire exponential term as a, and I know from math that this a is always going to be 0 because exponential functions are positive. Now similarly, I could do the second derivative of q with respect to xj square. I would get exactly the same value a. And even if I were to take the derivative with respect to xi and then xj, let's try to do that here. What would happen is that this minus xj would throw a negative sign here, and so I would get a positive sign. And again, I would be left with the same exponential function. So this also becomes a, and all these are of course greater than 0. So let's try to write this in a more nice form. So essentially all the second derivative terms are equal to a, and they are all greater than 0 because they all represent e to the power something, and that is greater than 0. So I can form the H matrix as this matrix of all the a values. Now one of the ways to find out the matrix is positive, definite or not, is the method which entails taking the leading principal minors. So by that I mean first we take this one, so that's determinant of A, then I take the 2 by 2 case, so that's going to be A, that's this particular determinant. Then I take the 3 by 3 case, so I get this 3 by 3 matrix determinant of that. And essentially all these should be positive or greater than 0. So the leading principal minor should be greater than equal to 0. So we see of course for the first value this is greater than 0, and for the determinant of size 2, determinant of size 3, and beyond that all of these determinants are going to be equal to 0. Now this tells us that this H matrix is positive semi-definite, and corresponding to the definition of convex function, this particular function is also convex. So essentially we have proved that the subparts of the function f of x, our test function, that is p of x and q of x, are both convex functions, and therefore the function f of x is a convex function. Now this is something which is very important and interesting, because what it would mean is that if I were to find a local minimum for this function, it would also be a global minimum, and in general the function would be very well behaved in terms of its minimum point, and therefore it would be a nice test function to check out our different algorithms with. Now if you are not familiar with the concepts of convexity, then do check out lecture 4 on convexity and also tutorial 4 on convex functions, and also make sure you check out my optimization playlist. If you are feeling bored during the weekend, maybe you can spend some time on reviewing the tutorials and lectures in the optimization playlist instead of wasting time on Netflix.